All right, testing 1, 2, 3. Testing 1, 2, 3. Got green bars down there. Got green circle over here. Looks like we are live. Greetings, travelers. How are you doing today? It is Wednesday, the 14th of April. I believe it's already mid-April. My goodness. Let's double check and make sure all of our inputs are doing okay. So let's get rid of that. There's our planetarium input. Very good. Leave that there. How about our universe? There's that. Very good indeed. All right. 2 for 2 on inputs. Let's take a quick peek. That's not what we wanted. That is the wrong thing. All right, we got our video input for this too. Perfect. That means we have everything we need to do our show. So, how are you all doing today? Chat? Of course, chat. When I say chat, I mean all of the chats, because we are live on Twitch and YouTube and Facebook all at the same time. If you are new to the channel, please feel free to stop me at any point, ask questions, ask for clarification, whatever it is that you would like to ask, please feel free to do so. Yes, that's what we're here for. If you think about a planetarium, you can sit down in a planetarium dome. Well, not anymore at the moment. But you can sit in a planetarium dome and ask questions at the end after you watch an entire show. This show is live on your phone or on your computer or on your TV, wherever you happen to be watching from. So feel free to just stop me whenever, because it's live. And it's on the intertubes. All right. Got a couple more websites up in the background here. Yep. All right, so we always start our shows with a little bit of like current events or just whatever is clever over here on Astronomy Picture of the Day. Mostly because I like the website. It's been around for years and years and years and years and years. It's been around since 1995. As you go back further, obviously the pictures get lower quality because the technology in the 1990s wasn't as good as it is today. As you can see, it's set up like an old website because it's just a bunch of links and dates. But once you click on a picture, once you click on the link, you'll likely get a picture, sometimes a video. There'll always be description at the bottom. Some of the pictures will have labels if you mouse over it. Sometimes the mouse over doesn't work till you click on it and make it bigger. This is what we looked at on Monday. This was the Lame Nebula. Confirmed Muon wobble remains unexplained. There's some strange stuff going on in particle physics. Things that are very, very small. And in the realm of particle physics, this particular wobble that was discovered the other day doesn't fit the standard model of what particle physics is and how we understand physics as a whole. Meaning that maybe our knowledge is incomplete, and with this muon being a wobbling muon. Again, we just don't understand it. Scientists that are, at these particle accelerators, this is the Fermi National Accelerator Laboratory, they don't have a clue what's going on as to why this is. So there, of course, the first thing you're going to check is, was there an error in the data? Was there an error in the collection? Something to explain it. And if that doesn't get explained away, then you keep that data and you start trying to figure out, why is that data there? How does it happen? We may be on a breakthrough of new science. Understanding how particle physics changes and how particle physics works. Cutting edge stuff. This is today's astronomy picture of the day. What is called the pencil let's try that again. Good thing we're live. We'll just add that in post, but we can't. The Pencil Nebula Supernova Shockwave. Very, very cool looking thing. Again, supernovas always end up looking interesting due to their chaotic nature. You see this wave of material. Now, when stars explode, they explode. Well, there's two ways stars can die. Some of them can die quietly and leave behind what's called a planetary nebula, or a ring nebula. I'll show you a picture of that in a second. Other ones die violently and leave behind huge, fast-moving clouds of gas and dust. They leave these weird waves, and over time they eventually start to slow down, cool off, and coalesce. There you go. So that's really cool, Pencil Nebula. Let's take a look at some other examples before we get into the show itself. Again, cool thing about Astronomy Picture today is that it's been around for a while, so there's lots of stuff you can look up. This is the Ring Nebula. This is a planetary-style nebula. As you can see, it looks very, very different. Really rounded in shape, almost egg-shaped. Stars that are like the Sun, or only slightly more massive than the Sun, will die and leave behind a little cloud like this. Rapidly expanding cloud, but a smaller, circular-style cloud nonetheless. When it's a star much larger, more massive than the Sun, you get an explosion. Explosion! Much more chaotic looking. Something like this. This is the Crab Nebula. It's actually out in the sky tonight. But, yeah, you can see a very distinct difference. Lots of high energy radiation right in the middle of this right here. Heavier elements being formed and fused. Some of them being split apart. Fission happening. Intriguing, the lives of stars. Again, that's an astronomy picture of the day. I'm not affiliated with any of these sites that I'm showing off, but I just wanted to kind of let that be where we start. The software we'll be using throughout the show today, there's two of them. One is called Stellarium. As you can see, it is available on Linux and Mac OS and on Windows. This is a open source free planetarium software. I do not have anything to do with them. I just like using the software because, one, it's free. Two, it's actually pretty robust for what it is. You can actually control a telescope with it if you had one connected. Other software we'll be using throughout the show is this. This is Universe Sandbox. You can find it over on Steam. You might even be able to buy it directly through them. I'm not sure, but I picked up mine over on Steam. There we go. Humble Bundle. There is a chance to use it on Oculus Rift. So if you want to fly through space with this all up in your face, virtual reality style, you can do that. We'll look at that in just a little bit. That's this software right here that we were looking at, actually that I was looking at a little while ago. And you can change simulations and things like that. This happens to be the solar system simulation, and we'll talk about this in just a little bit. Stellarium, you got a brief... Come on, there it is. Stellarium, you got a brief look at when I brought this up. This is our planetarium software. You'll notice that there are labels along the edges. You got east, south, west, and north way back here. north, now actually at the front of the dome. So this has all the cardinal directions, and this is actually looking out at the sky the way it is right now, from my point of view. Now, depending on where you live, certain stars may be higher up in the sky, certain stars may be lower in the sky, depending on your distance from the Earth's equator. But the star groupings, the constellations, the shapes that they appear to make, well, those are universal. Doesn't matter where you are on the Earth. They will look the same. But again, their altitudes above the horizon just depends on where you happen to live on our beautiful planet. So I'm going to put things in motion, let that start moving. We're going to go back to our browser and talk a little bit about... Not Universe Sandbox, we already talked about that. We're going to talk about that later. We're going to talk about Mars real fast. The Mars Ingenuity helicopter is what people are calling it. It's really just a little drone. There's a beautiful selfie from the other day. That was scheduled to actually fly, to lift off the planet Mars and fly around for a little bit. That was scheduled on Sunday evening. And then that got canceled and pushed back to today, and now they're pushing that back again till next week because there is a weird software issue that was discovered during pre-flight tests. This little thing only weighs about 4.5, 5 pounds, something like that. It's just above a kilogram and a half. Very, very lightweight. The goal is to try to get this thing in the air before it freezes, because it is very cold on Mars at night. But, yeah, we'll see when they get it up. It does look like a really cool little craft. I hope it works. I really want to see those photos. But if you haven't been keeping track, this landed on February 18th. This is the Mars Perseverance rover, which had this little helicopter attached to its belly in a protective case, of course. And now it's no longer in the protective case. It is now alive and well on the surface, being powered by the sun, that little solar power panel on top of it. The rover itself, however, is not solar powered. The rover is nuclear powered, so it will run as long as it needs to, as long as the wheels don't break and get it stuck somewhere. So yeah, we'll keep an eye on this, and we'll hopefully get to do a live stream when that does occur. Take a look at some photos real fast of Mars. This is from the mast cam. Can I not get a bigger photo? Okay. We could, but I think if I download it, it's just going to be weird. But whatever. That's fine. Anyway, this is all free to find, free to download. Mars Perseverance rover, mars.nasa.gov, for you to get these photos. Some of them are out of focus. Wonderful. Alright, so that, no current events there. Let's go back to our planetarium and begin. So again, we are looking at the southern part of the sky. Already you will notice that there are two bright objects right along this region right up in here. We've got the sun and the moon. The moon is out right now. Of course, the moon orbits around our planet Earth, and the sun is the anchor point at which the entire solar system orbits around. We're going to do a whole virtual tour of the solar system in just a few moments. So please stick around for that. The show is kind of free form. We do have some ideas that we do always like to convey in every show. The repetition is good. You will hear some of the same ideas, which is fine. Again, if you have any questions, feel free to stop me. I'll clarify them as best I can. There are some questions I might not be able to answer, because there are some questions that science has yet to answer. And that's just the way it goes. Looking at this part of the sky, we see the sun and the moon. We see the moon in a small, what's called a waxing crescent. It's a small sliver like this. Beautiful, beautiful to see. Bright side on the right side. You'll see it above the horizon very clearly right at sunset. We'll talk about moon phases in just a little bit. Now we're going to do something that I do not recommend you do, which is we're going to look at the moon, at the sun, I should say. The moon is totally fine. I just totally screwed that up. The moon you can totally look at. It's just reflecting sunlight, so it's not a big deal. However, the sun itself is very, very bright. You do not want to do what we're doing right now, which is staring at the sun or even zooming in on the sun. Because that's how you can hurt your eyes, you can hurt your camera, you can hurt your phone, you can hurt your telescopes, depending on what you're using to look at the sun. Now, this is not exactly what the sun looks like right now. This is just kind of an example of what the sun usually can look like. These dots are called sunspots. They are colder areas of the sun. When it comes to stars, the sun is an average star. It's considered a yellow dwarf star, but it's our star. It's our favorite little star. And we use it to kind of measure other stars, so it's our test bed as well. What we know about the way the sun works is that there's convection, there's a core deep inside, and it's a big nuclear furnace. It's fusing hydrogen gas into helium, and that releases a little bit of energy, and it happens a lot of times in the core. Hence the nuclear reaction. It's a chain reaction, it's always happening, and so that releases a huge amount of energy. It travels through the sun itself. The sun, like an ogre, is like an onion and has layers. Eventually, that is a Shrek reference. Yes, chat, you're correct. That is a Shrek reference. The surface will sometimes have these bubbling features going on, but there will be areas that are a little bit cooler. There's actually a lot of magnetism happening with the sun. Let's actually take a look at Universe Sandbox. We'll look at the sun up close here, and you'll see that convection going on. You see it bubbling up to the surface right in here. This is actually kind of the process of how it works, and it happens all around the sun itself. The sun, doesn't matter which way you look at it, it's going to look very similar. It's going to be glowing, obviously, because it's releasing all that energy. So if you can't stare at the sun, how do we know all these different things? I mean, you could, but it's going to damage your eyes. Well, there's this. This is called the Solar and Heliospheric Observatory. This is an orbiter in space. It is closer to the sun than the Earth, so it has a nice front row seat, always staring at the sun. This is a literal current photo of the sun. This is from today. And as you can see, there's not all that much going on with the sun. The sun actually has a cycle of activity. Every 22 years, it's either fully maximum or fully minimum. So half of that's 11 years, so you go from maximum to minimum in 11 years. We just hit minimum, I believe, last year. And so now we're slowly exiting out of solar minimum into solar maximum. What does that actually mean? Well, it has to do with these little dots. These are sunspots. Now, really quickly, let's take a look at the sizing chart down here. Earth is about the size, let's see, I can fit my mouse inside of Earth right there. And as you can see, Jupiter is 10 times, a lot bigger than that, 10 times that. These sunspots are the size of our entire planet. Now, they may not look like much. They're just little dots in what we can see, visible light, so to speak. Soho has multiple instruments on board, multiple cameras, that reveal a huge amount of detail and a huge amount of information about the sun. So let's take a look at that real fast. Here's, again, more of what we could probably say we would see if we were able to look at the sun without hurting our eyes. Bright yellowish disk, and you see again sunspots looking like little darker spots. But this is what our eyes can see, and remember, just a few moments ago I said these areas are very magnetic. If you look at a magnetogram, something that's measuring the magnetic fields of the sun, you see very interesting features. You can pick positive or negative, doesn't matter which side you want to pick. which one's dark, which one's light. All it matters is that they are opposite charged, and right around the sunspot you see a huge amount of activity. You see lots of little patches that are also very similar, but it's very, very active around the sunspot. That in turn means that there's a lot of activity happening around the sunspot. To see that, we must look. I see this is a few days old, so that doesn't work. The sunspot has moved. Sunspot should be sitting here, but this is a photo from the other day. As you can see, that's the same set of sunspots, and you see there's actually activity happening very near it. There's actually material being pulled up from the solar surface, and it's being transferred up into the solar atmosphere, what's called the corona. You see it once again down here, and you see this activity all along the edges of the sun. Let's take a look here. You can see, again, little bits of material being blown off into space around here on the edges. When it's on this side, it's actually more towards us, which can be concerning. When it's towards the edges, it's not too big a deal because it's just kind of being blown out into space. Let's go to this photo. There we go. And again, as you can see, very active near the sunspot. And actually, this one shows a lot more activity along the edges. This is in hydrogen alpha, which is the excited state of hydrogen, which gives off a very distinct red glow. And we see a lot of activity with the sun in this frequency. We'll talk about frequencies in just a little bit. You see a solar flare happening there. You see some more filaments, as they're called, kind of being stuck up around here. Very, very cool. Very warm, I should say. If we want to see the corona, we must zoom out further. The corona is the outermost portion of the sun. This is where you see a lot of activity. Now, this image, let's explain it real quick. The white circle is the sun itself. The surface of the sun ends at the white circle. The dark circle is the sunblock, so to speak. It is a shield blocking the camera's view so that it actually can see the surface of the sun, or the corona of the sun, without having excess brightness blinding it. And you see all of these jets kind of shooting out. These are coronal mass ejections. They are a huge amount of energy being chucked out into space. Sometimes, especially on this zoomed out one, you actually have the arm that holds the shield right here. The shield itself, and the sun again is the white circle. In this picture, you actually get a couple of planets. You got Mercury over here on the right, and you got Venus over here on the left. The two innermost planets of the solar system, they are very close to the sun, and on occasion, they will make an appearance in this particular camera. And actually, even Jupiter, Mars, Jupiter, Saturn, Uranus, Neptune, sometimes they pop up in the background, but they're nowhere near as bright as these two when they are in the image. But again, you see material being blown out into the space around the sun. There was a tweet. There it is. This is from, I believe, yesterday or today. April 12th, so 2 days ago. Titled, Finally, Some Action in the Sun's Corona. Take a look at that. So what we have here is a loop showing coronal mass ejection, actual flares being blown out into space. Again, you don't want to be necessarily in the path of this, because that would be very, very bad. Sometimes these explosions are actually pointing towards our planet Earth, which also is bad. When that happens, the Earth gets bathed in a large amount of radiation, which bounces off the radiation belts around our planet, the Van Allen belts. But there is some material that does make it through that excites the north and south pole of our planet, and you get actually, this was not planned, but you get stuff like this. You get the Aurora Borealis, the northern lights or the southern lights. These are particles coming from the sun and energizing the atmosphere of our planet. Very, very cool. That pays sweet. All right, so there's a little bit about the sun. Let's come back to Stellarium. There we go. And let's let the sun set. Speeding up time. We're going to stop right here during twilight, and we're going to talk a little bit about how things work with sunlight and our atmosphere. Our atmosphere blocks a lot of radiation from the sun. It does let through what we call visible light, so I want you to think about the rainbow: red, orange, yellow, green, blue, indigo, and violet. Those are what our eyes can see. But as it turns out, there are many, many forms of light that our eyes cannot see. So to see those forms of light, we actually have to build different telescopes and different observatories to see them. During the daytime, the bluish light filters through and makes it through our atmosphere without any problems, hence why the atmosphere turns blue. During the morning, when the sun rises, and during the evening, when the sun is setting, the longer wavelengths, the red, orange, and yellow, they filter through a lot easier. So the sky changes color to those particular colors. During twilight, during twilight, the first things you usually see are going to be the moon and planets, and then after a few minutes you'll start to see stars appear in the sky. Stars will twinkle, planets do not. Again, stars are coalesced balls of gas and dust and plasmas undergoing a fusion reaction in its core. Now, depending on what they're fusing, they may or may not be called a main sequence star. A main sequence star is a star that, well, it was born the way it is, and it's currently fusing hydrogen into helium gases. We'll talk about the main sequence of stars and star birth and star death in just a little bit. In fact, I should probably bring that up in the background here. Again, feel free to stop me at any point and ask questions about anything you'd like, and if I can answer them, I will. If I cannot answer them, then I won't, because I can't. Zoom in a little bit on that one. Zoom in a little bit here. There we go. Okay, let's come back to our planetarium. I know you can't see what I'm doing. I'm doing it off screen, and that's totally fine. So again, here we are looking at sunset tonight. The moon will be low in the western horizon. Only one planet is out tonight. One planet you can see with a telescope, that is. And we'll talk about that in just a second. So here we are. The sun is gone from the sky. It's about 8:45 now. And this is our sky. The moon hanging low along the western horizon, again looking like a crescent moon, something like this. And actually looks like this is some earth shine if the moon is lit up slightly, even though there's no light hitting this side of the moon. If you can see it, it's actually the light reflecting off the surface, hitting our planet and our atmosphere, and reflecting back up and illuminating the moon. Let's leave that right there. Let's talk about the moon. Now, the moon is our only natural satellite orbiting around our planet Earth. It is a rocky world. Orbiting around the Earth. That is the sun. Let's back away from that. Actually get rid of everything and just have the moon and the Earth. Here we are, looking at the Earth now. The one thing I haven't really talked about yet is the Earth at night, which actually looks something like this. If you look very, very closely, you can see that there are, well, there is a problem with what's called light pollution. Light pollution is actually caused by our cities, the lights around our streets, You see cities in very distinct detail. Let's slow it down slightly. There we go. And again, you can see some of these cities very distinctly. There's Moscow, you got Rome, you've got London and Paris, and Madrid, Cape Town, South Africa, Rio de Janeiro, Mexico City. There's the entire eastern United States. So again, where you see all this brightness, yeah, that's where we live as humans, but you'll also notice there's a huge amount of what's called light pollution, so you don't see the sky very well. You do need to be far away from the city lights to be able to see the sky the way it's meant to be seen. Let's take a look at our moon. Closer. There we go. All right, here we are looking at the moon itself. The moon, again, early natural satellite. I'm going to speed things up a little bit. The moon does orbit around the Earth, and as it does that, it does also rotate on its own axis. From here on the Earth, we don't really notice it. Every time you look at the moon, you're looking at the exact same side because it's what's called tidally locked. The gravitation of the moon and the gravitation of the Earth have, over time, forced the moon to keep the same face looking towards us at all times. The darker splotches along the surface of the moon, we call them the seas or the mare. People thought they were filled with ocean. They were oceans of water filled with water, but they are not. They were actually lava pools that eventually solidified over. So they are a little bit younger. You do also notice that there are some craters in these younger areas. So these are fairly younger craters on the surface of the moon. Lots of different hypotheses about how the moon was formed. Some say the moon was captured. Others say that the Earth was hit by something during early proto-Earth time. And that then ripped a chunk of the Earth off, and then that formed into the moon. Let's speed this up a little bit. As you can see, we are orbiting around the Earth. The Earth should be off in the distance. Where are you, Earth? There you are. You're back there. The back side of the moon, what people like to call the dark side of the moon, that's not totally true. The back side of the moon gets sunlight during what is called new moon phase. So from here on the Earth, when you look at the moon during new moon phase, you get this. The moon is in the sky at the same time as the sun, so all the light bounces off this, the back side, what's considered the, quote, dark side of the moon. It really just means it's the far side of the moon. If we were to watch from above, you see this beautiful dance happening. The Earth kind of has its own little circle that it goes on. And the moon goes around the planet Earth. Speed things up a little bit. And all of this, of course, is moving around the sun. There are times where the moon is closer. There's apogee and perigee, where the moon is either closer to the planet Earth or further away from the Earth. So that's what gives you the quote-unquote supermoon status for the moon itself. This is actually a lot easier seen if we use the moon phase simulator. Not the distances, the slight wobble in the orbit, but the actual phases, the way they truly work, is best seen through, if I can find it, there we go. So here we are looking at the north pole of the planet Earth, right in the middle of the screen here. And there we are, humans on the surface. There's the moon, and the sun, of course, is off to the left in this case. Put a little pink marker so we can see where the center of the moon is, and you'll see the moon always keeps that same face looking towards us. When you go from new moon to first quarter moon, you notice It goes a quarter of the way around the planet, and the bright side is on the right side. We call this a waxing moon. Bright side on the right side. Once you get 1/4 of the way around the planet, you enter into, again, first quarter phase. Past that, you start to have the gibbous phase. It's not full, it's not a crescent anymore. It's just kind of getting bigger and bigger and bigger. Up until you get to full moon. So if new moon was just a few evenings ago, a few days ago, full moon will be in 2 weeks. This entire process takes an entire month. It's actually where the word month comes from. It's from the cycle of the moon, going from new moon to full moon and back again. This is a full moon. You'll notice the moon rising up at the exact same time the sun sets. They are opposite each other in the sky. And then the phases go in reverse. You go to a gibbous and then back to a crescent, but we call them waning. When the bright side's on the right side, that is a waxing gibbous. When the bright side's on the left side, that's called a waning gibbous or a waning crescent, depending on the phase, of course. Third quarter, or last quarter moon, the moon has gone 3/4 of its way around our planet Earth. And then that cycles around to new moon, and the cycle begins again. Now, the sun and the moon and 5 other objects are called the classical planets. Now, the moon is not a planet. The moon is a satellite. The sun is not a planet. The sun is a star. But to ancient astronomers, they didn't understand that. When they looked up at the stars, at the sky, they saw all these little points of light that only seemed to change with the seasons. The quote-unquote, oh god, that's not what I wanted to show you yet. None of this is what I wanted to show you yet. Abort mission, abort mission. There we go. When you look at the sky, you see these shapes, these patterns. Various cultures came up with their own sky stories to come up with these patterns. Many of the ones that we have on the dome right now, we call these Western astronomy constellations. Many of these have been around for millennia, going back all the way to ancient Egypt, before the pharaohs, with the pharaohs, even possibly going back further than that into like Sumeria and Assyria, those Mesopotamian cultures, the cradle of civilization as we call it. So these are very ancient stories, and they all kind of change names. Maybe the star shapes remain the same, but the stories or the names around them change. But these are what we call constellations. There are 88 of them in the sky. If you combine the northern hemisphere and the southern hemisphere, these constellation shapes, again, are relative to Western astronomy. There are different shapes if you look at different cultures. So let's say, I always pick Chinese because that's very different. There we go. Same exact sky, but very, very different number of constellations. We're going to be using the Western sky in our planetarium. Of course, there's Native American, there's Inuit, there's First Nations, there's Siberian, there's Sami, there's Norse mythology. There's all these different ones that you can learn about. But right now, we're just going to be using the Western one, which is this. So these shapes all remain the same. Of course, as the seasons change, some constellations are visible, some of them are not. For us today, we understand it's because as we orbit around the sun, we appear to look at different portions of our Milky Way galaxy. The Milky Way galaxy is a huge collection of stars, gas, dust, and material, dark matter floating through the space. You'll see it as this little cloud in the background. We'll talk about galaxies in just a little bit. But again, ancient cultures looked up and they saw all these objects, these shapes, but there were some weird objects that seemed to move around. The Greeks called these objects the stars, asteris, but the ones that moved around, that included the sun and the moon, they called asteris planetes, which means wandering star or vagabond star. That's where the word planet comes from, planetes. Wanderer. Of course, the sun and the moon are no longer considered planets. The sun, again, is a star. The moon is a satellite orbiting around our planet. And we've also got the planet Mercury, Venus, Mars, Jupiter, and Saturn. That is a total of 7 objects. We call those the 7 classical planets of astronomy. And this all has to do, actually, if you think about it, look at your calendar. How many days of the week are there? There's 7 classical planets. There's 7 days of your week, each one named for a planet. So Sun, Sunday, Moon, Monday, Tuesday is for Mars, Wednesday is for Mercury, Thursday for Jupiter, Friday for Venus, and Saturday is Saturn's day. There's some language issues going on there. If you speak any sort of Romance language, Spanish or Italian, the names sound a lot more familiar. So like Friday is Viernes in Spanish. Viernes sounds a lot like Venus, doesn't it? Miércoles, Mercury, that's Wednesday, and then Jueves, Jupiter. You can kind of see where that all comes from. Now, again, a month is talking about the cycle of the moon. So we have 12 months of the year. Where does that also come from? Well, it has to do with astronomy as well. There are 12 constellations of what we call the zodiac, in which the sun, the moon, and all the planets appear to travel through the sky. You've probably heard of some of them, such as Taurus the bull, Gemini twins, Leo the lion, Cancer the crab, not in that order, I screwed that up, Virgo, Libra, Scorpius, Sagittarius, Pisces, Aquarius, Capricorn. Those are zodiac constellations. These are the constellations in the sky that the sun and the moon and all the planets happen to travel through. It helps you know which time of year, which season it is. If you can keep track of where these constellations are and which constellations are not up, because they are opposite of something in the sky. And in the springtime, maybe you're looking at one constellation. For example, tonight, since it's springtime now, we can say Cancer the crab is right here, right smack dab in the middle of the southern sky. And this is in April. But in August, Cancer will not be here. Cancer will be further towards the west. Something else will be in this exact spot, and you can kind of tell where the constellations are and how they cycle around if you observe for a year, maybe 2, and draw some really accurate sky charts, which is what astronomers and navigators did very often. Now, astronomy is a study of the sky and study of how these things all move around. Astrology has to do with, where the objects are, the planets are in these particular 12 constellations and how that relates to you. That's not exactly a science today. Some people would claim it is. Long ago, however, astronomers also had to be astrologers. If you were a royal astronomer, you also had to be able to kind of divinate using the sky. Be able to tell the future, or, tell your king or queen great things will happen because certain objects are happening, certain things are happening in the sky. Now, why do the sun, the moon, and all the planets happen to be on this flattened out plane? Well, the answer is the way physics works. How many of you have made pizza? When you make pizza, you make a ball of dough, and then you knead it, and then you start to spin it around and around and around, or you toss it while spinning it. And what happens as that happens? What happens as that happens? What happens as it happens? You start spinning it around, and everything starts to flatten out. Notice the orbits of all the planets appear to be on a flattened out plane. This is the plane of the ecliptic. If you were to draw that line out, that would be the line going to all the zodiac constellations. In three-dimensional space, as you can see, not all the planets are exactly at the equator of the sun, but close enough. The 4 innermost planets of our solar system we call terrestrial planets. Terra meaning Earth-like. Mercury, Venus, Earth, Mars. 4 inner rocky worlds. Mercury is the messenger of Roman mythology. Hermes in Greek looks something like this. Not too many orbiters have been to Mercury. It's really, really hot. So it does not bode well for things orbiting around this planet, let alone landing on it. The surface temperature very, very high. Not a pleasant thing. We don't really know all that much about Mercury, to be completely honest, because we don't really visit it or pay too much attention to it because it is so hard to get to. Venus, the next stop in our solar system tour, is Earth's evil twin. It's about the size of our planet Earth. but it is very, very different from our planet. It has a very thick atmosphere based around carbon dioxide, traps a huge amount of sunlight, so the surface temperature is always about the same, which is about 800 degrees. Not a pleasant thing to endure, I would say. 800 degrees Fahrenheit, so that's about 465 degrees Celsius, something like that. It also rotates the wrong way, so the sun would rise in the west and set in the east, which again is very, very bizarre. Also, it rotates the wrong direction for reasons we don't know. It does so very slowly, again, for reasons we really don't know. It orbits in the same direction as all the planets, but it spins the wrong way. Very, very strange. Let's look at Earth, which is right here, which we've already looked at. We're going to do it anyway. Also do something fun. We're going to add the moon in. So you can see, as we orbit around the sun, the moon also kind of makes its own orbit around our planet. Always kind of trailing behind and catching up, thanks to gravity. Let's go to Mars. Mars, the next planet out, the last of the terrestrial or Earth-like planets. Mars is out tonight. We'll look at how to find it in just a second. Mars is interesting in the sense that it's kind of Earth-like, but smaller. It doesn't have liquid water on its surface anymore, at least that we don't think. There might be some trapped under the surface. Mars is about half the size of the planet Earth, but it has a very Earth-like day. It's 24 hours and 37 minutes long. We call it a sol. It's tilted over like the Earth is, so it has seasons, it has ice caps at the north and south pole of the planet. It has very interesting land features. I'm going to sneeze, give me 1 second to mute myself. Pollen, you will be the death of me. Oof. So, stopped in front of us here is the huge crater. This is a huge canyon-like structure. This is Valles Marineris that we see along the surface of Mars. If you put it here on the Earth, it would stretch across the entire United States from San Francisco all the way to New York City. You've also got these interesting volcanoes very nearby. These are the Tharsis Montes, as well as Olympus Mons. These three shield volcanoes here are the Tharsis Montes, the Tharsis Mountains, and then Olympus Mons. Now, Olympus Mons is the size of the state of Arizona, the state of New Mexico, the state of Colorado, or the state of Utah. Pick one. This entire volcano would fill up that entire thing. It also is slightly raised above. You can see a bit of shadow over here. It's actually a couple of kilometers above the surface, and then it begins to rise. So it's almost like a big pimple kind of punching up from the surface of Mars. It reaches up about 25 miles, so, 40 kilometers or so. Above the surface, up into the atmosphere, and actually slightly above the atmosphere. It is the largest volcano in the solar system. Happens to be on Mars. Once you pass Mars, you enter into the realm of the asteroids. All of these little circles out here represent asteroids. They are not necessarily planets themselves. They are considered mini planets. Some of them look like little orbs of iron or rock. Various rocks all kind of piled together. Some of them are named because they have been known for a very long time. Again, some of them are rounded, so we call them minor planets or planetoids. I'm trying to find one that looks like a football, but I might not be able to do that. That's okay. Some of them are kind of potato-shaped or football-shaped. And that happens, and that's okay. That's alright. Let's just keep going. Back to our tour of the solar system, shall we? Let's enter the realm of the giants. The giant planets, or Jupiter-like planets, the Jovian planets, are out past the asteroid belt. These planets are made of gas. They spin, they rotate very, very fast. They're very large, gaseous worlds. Let me pause this for a second. Jupiter, Saturn, Uranus, and Neptune all have rings. There we go. You can kind of see a faint ring along the outside here. Jupiter's is actually made of dust. Saturn's is made of gas and ice, mostly ice. Uranus and Neptune, they have older, colder, and not so reflective ices. Unfortunately, so they aren't as pretty. But here you are, you do see Jupiter and its great red spot, very prevalent right in here. This is the huge storm-like structure in the upper atmosphere. It's been around since, the early 1600s, I should say. It was discovered by Galileo Galilei in 1610. Jupiter has a large family of objects around it, and by that I mean it has a large family of moons. Let's see if we can bring those up here. There we go. As you can see, they're all in various orbits, and they can actually be kind of far away. These are all gravitationally bound to Jupiter in some way. You can see it's a huge cloud of objects around Jupiter. But the four that we like to talk about are called the Galilean moons, or the Galilean satellites. They are named for Galileo Galilei, who was the first to discover them. Again, in the year 1609, 1610, Io is the closest of the four. The Io, or Io, is a volcanic world. This surface changes constantly. It's too close to the planet, and so as it orbits around, it gets stretched and pulled by Jupiter on one side, and actually by another moon called Ganymede, which we'll get to in a second. They actually kind of shred this little moon apart, shoots volcanic material out, so it's actually making a little ring of dust around it. And eventually it will be slowing down to the point where it's going to get captured in what's called the Roche limit around the planet, which will then pull it in and shred it apart, turning it into another asteroid field around it, so it's going to have another ring. This is Europa. This is an icy moon. Its crust is 10 miles, so like let's say 20 to 25 kilometers thick. Under this surface, because of the gravitational pull of Ganymede and the gravitational pull of Jupiter, we're pretty sure there's a liquid water ocean. Is that ocean fresh water or salty? People think it's salty. So if there's a saltwater ocean under this surface, is there life? Is the water too cold? Maybe. Are there vents or something below heating up the water so that something could live? Maybe. We don't know. We need to explore Europa. It is an intriguing moon orbiting around Jupiter. This is Ganymede, the largest satellite in the solar system. If it were orbiting the sun, it would actually be a planet. It's a little bit bigger than Mercury. It's around the size of planet Mercury. But it's in orbit around Jupiter instead. Where's my last target? There's Europa, Ganymede, Callisto. There you are. Callisto is the fourth of the Galilean satellites. Also an icy moon. Very heavily pockmarked. Intriguing world indeed. And again, there's so many other worlds around Jupiter, as you can see. We could spend a whole day going to each one and try to talk about them, but we're going to keep moving. Next up is the planet Saturn. Saturn always shows up without rings, and I can't figure out how to fix that. But I do know that you can add the rings, so give it a second, and there we go. The rings are slightly visible. Just not as beautiful as I would hope. There we go. Let's just keep adding rings till we have a ton of them. There we go. Now we have the rings around the planet, but I think I may have just broken everything. There may be too many particles now. In any case, this is Saturn. It does have a ring system. Those rings are made of, again, ices and rocks covered in ice. There is a gap called the Cassini division in the ring system right out here, which we named after astronomer named Cassini. There's also the Encke Gap, which is also named after an astronomer. These rings you can see clearly through even a small telescope. I'm going to reset this if I can, because I think I broke it. There's too many particles, but that's where the rings are. That's how they kind of orbit around the planet. Let's see if we can dump this and reset it. So as to keep using it. It's actually not a function in my computer. It's just when you add that many particles in, because I kind of went ham on the particle additions there. I guess I broke it. Whoops. All right, let's go to Saturn. Boom. Let's pause Saturn. Let's add in maybe 2 rings, 2 sets of rings. Saturn, add ring. 1, 2, 3. Okay, that's enough. So you can kind of faintly see the rings now. You can see that they are at an angle. They're along the equator. The planet does have an angle to it. Around the planet Saturn, you do also have satellites or moons. A huge number of them, in fact. There we go. The largest of which is called Titan. Titan is the second largest moon in the solar system, but it is the most intriguing in the sense that it is the only moon in the solar system that has an atmosphere. You can actually see light reflecting through that atmosphere, or diffracting through the atmosphere. This is an atmosphere made of this is made of methane. There's actually liquid methane oceans, or lakes, on the surface. The Huygens space probe a few years back actually did pierce the atmosphere and eventually crash landed on the surface, and you actually saw huge mounds of ice, likely methane ice, and actually liquid methane rivers and lakes. Very, very strange world. Again, it orbits around Saturn, which is right back here. The other moon I wanted to talk about while we're here is we're going to be looking for Enceladus. There you are. Enceladus, in a way, is like Europa. It is an icy moon that has a very thick crust. You can see it's pretty close to the planet, in this case Saturn. But we know there's liquid water here. How do we know there's liquid water? There are geysers. You see these cracks on the surface? Some of these cracks actually have geysers of water shooting out. Speaking of water, if you haven't done so, you should probably hydrate. You've been sitting around watching this show for about an hour now. Make sure you hydrate anytime you stream, or if you're watching something or gaming for a good long time. Always make sure you hydrate. But there's Enceladus. Let's zoom away from Saturn, and it's very large. You can see these are all gravitationally bound. They can be very far away, but still be gravitationally bound to a planet. We're looking for the next planet out, so we're going to Uranus. Now, Uranus is another question mark in our solar system. Uranus does have moons, and it has rings. Let's add some rings to Uranus. And what do we notice? Well, one, the rings aren't very prevalent. Let's add the moons. Maybe that'll help. The moons are in the same plane as the rings. What do we notice? This entire world is on its side, and we don't know why. Uranus is such a strange, strange world. But we don't study it very much, because it's pretty far out, hard to get to. It's only been visited by, I believe, 1 space probe. Voyager 1 and Voyager 2 each visited either Uranus or Neptune on its way around. No, that's there. We can finally kind of see the rings. Got to get to the right angles here to be able to see the rings properly. They're very, very thin. They are made of dust. They don't reflect back a large amount of sunlight. But again, Uranus is on its side. We don't know why. There, you can kind of see the rings here as we get a little bit further away. Let's zoom out further to the planet Neptune. Neptune is the last of our gas giant worlds. Neptune, people like to call a frozen world because it is so very far from the sun. It does have moons. It does have a ring system as well, but I don't see the option to do that. It doesn't have very many moons, but it does have some. So you can see here. Interesting, of the moons of Neptune is Triton, which actually orbits the planet the wrong direction, implying it was actually a captured moon. Neptune has a dark spot, not in this image unfortunately, but it has a dark spot like the Great Red Spot, but it's dark. And it changes positions. Sometimes it's in the southern hemisphere, sometimes it's in the northern hemisphere. We don't know why. Again, one of these worlds we don't really study all that much. Once you pass Neptune, you enter a realm called the Kuiper Belt. These are filled with objects that we call the trans-Neptunian objects. They are objects out further than Neptune. They include Sedna and Quaoar and an object called Pluto. We don't have any data on Sedna, so it's just a blank object. That's just wonderful. Pluto used to be a planet in some places. Here in New Mexico, for example, people still consider Pluto to be a planet. It's not officially a planet anymore because, as you can see, its orbit is very, very strange. Pluto's orbit actually, because of the way it is, will sometimes be closer to the sun than Neptune is, which is very strange. All the other planets seem to stay in their lane. Pluto does not. Pluto also has not a very large stature to it. Pluto does have actually a couple of satellites orbiting around it, including Charon, which is tidally locked to the planet Pluto, or the object known as Pluto. There we go. So these two actually keep their face looking at each other at all times, and that's very strange. You'll see there's actually five objects gravitationally bound to Pluto. So why it's not officially a planet? Well, it's mostly it doesn't fit the gas giants. It doesn't make sense. Maybe it's just a really oversized comet. All the comets live out here. That is our tour of the solar system. Let us return to base here. There we go. Let's go back to our Planetarium software. Again, feel free to stop me. I see some chatter in chat. I appreciate that. Hopefully I'm answering these questions as we go along. Even if I don't necessarily fully acknowledge them, I am trying to weave them into what I'm talking about. Going back to this, so that entire side there was just to talk about why the sun, the moon, and all the planets are on this nice flat plane. Let's take a look at the sky tonight and actually learn a little bit about finding your way around. The full moon, if you were to hold your hand out all the way, hold your arm all the way out, look at your fingertip, that fingertip, your index finger, that's going to be considered about a ½ degree. Depends on the size of your hand, of course, but the sky is broken up into various degrees. 180 degrees from horizon to horizon, so from west to east. And it's all kind of based around the North Pole, so you can see everything starts there, goes all the way around, so things are measured in degrees. Excuse me one moment. All right. Some objects, we can actually use our hands to kind of measure our way around. So your hand is about 5 degrees wide if you look at your palm. And then again, your index finger, it's about a ½ degree from your index finger tip to your middle knuckle. That's about 2 degrees. We're going to look around through the sky. Oops. So if you see this little line start to appear, this actually is a little line making device, but it also shows you degree measurements. So the belt of Orion, which is what I'm trying to highlight now, is about 3 degrees wide, so you can cover up the entire belt of Orion with your outstretched palm. Okay, let's start with Orion, one of the oldest constellations in the sky. This is the Great Hunter, sometimes holding a club and a lion pelt, other times holding a sword and a shield. Lots of different stories behind what he could be. To me, he's the easiest thing to find. He's an easy pointer to find your way around the nighttime sky, from the early winter through the early spring, which is where we are now. Now, Orion and the constellations around him will all be going below the horizon very, very shortly, and not just for the evening in our planetarium, but I mean in reality. We're no longer in spring, in winter time. We are now entering into spring, and these constellations will be leaving the sky. So in just a few weeks, Orion will be too low to the horizon, and you won't actually be able to see it at all. It'll be replaced with other constellations, which we'll talk about as we get to them, as the sky continues to change from our point of view. The belt stars are helpful pointers. You can draw a line through them towards the western horizon and find 2 open star clusters known as the Hyades, the V of stars making the face of Taurus the bull, and the Pleiades, the 7 sisters or Subaru. They hang out on the back of the bull. There's Alcyone, one of my favorite stars. That's why I named our cat after it. Aldebaran is the eye of the bull. It's a bright reddish orange colored star right in here, this V of stars. We'll talk about star colors and what that truly means in just a moment. Coming back to Orion, you see the 3 belt stars are very blue. We're going to draw a line through them to the east and find an extremely bright blue star. Go this way. Boom. We now have the heart star of Canis Major, the big dog. This is Sirius. Seriously, it's very, very bright. Canis Major is one of Orion's 2 big hunting dogs. Hangs out just behind him. Above both Orion and Canis Major, it's going to be Canis Minor, the little dog. Now, what I find interesting about that... Let's get rid of that. There we go. What I find interesting is that it's only 2 stars, so it's a hot dog or a dachshund in the sky. Draw a line from Sirius to Orion's shoulder, known as Betelgeuse or Betelgeuse. Literally means armpit of the giant. And complete a triangle up this way. Right above Sirius, you find Procyon. Now, these are about 25 degrees apart from each other, so the distance from Sirius, if you put your thumb over Sirius and then stretch your arm out, stretch your hand out, your pinky finger would be over here by Betelgeuse, and the same thing happens with Betelgeuse to Procyon. So you can see these stars are pretty far apart in the sky. They may look close together on our dome here, but they are actually pretty far apart in reality. This again is the triangle in the sky known as the Winter Triangle. 3 very bright stars you see during the winter months, but we are no longer in winter, and so these will all be getting lower and lower and lower in the sky every evening. In just a few weeks they'll be gone, and you won't see them again till late October-ish for easy viewing. Above Orion, you will find the twins known as Gemini. Orion's knee star is named Rigel. Draw a line up through the belt from Rigel past Betelgeuse, and you will find 2 stars that are about the same brightness, but they're slightly different colors. They're about 4.5 degrees apart, so they're about the width of your palm once again, apart in the sky. One is named Castor, the other is named Pollux. These are the twins known as the Gemini twins. Above Taurus the Bull and above Orion, you will find the planet Mars. Again, easier to find Taurus the Bull first, which we did earlier. We just do the belt stars, find the V stars, draw a line straight up from the V. You will find a non-twinkling red object. You will find the planet Mars sitting between Taurus the Bull's horns. There it is. Told you we'd find Mars. Mars will not be twinkling. Mars is not all that bright. Venus and Jupiter are the two brightest of the planets you can see during the morning or the evening. Mars will just have a very distinct reddish colored glow to it, hence the name after the god of war, blood and fire and things associated with war. Cancer the Crab, really, you need to be in the middle of nowhere to be able to see it. It's a very, very hard constellation to find. Leo the Lion, however, is not a hard constellation to find. There's a nice bright blue star at the bottom of a question mark. This question mark is right in here. The bright blue star is named Regulus, and actually looks more like a sphinx, doesn't it? Again, one of these older constellations has likely been around since pharaonic times in Egypt. Let's take our planetarium and turn it around. We're going to look north for a second. In the northern sky, we've got a lot of constellations that never really set. We call them circumpolar. They circle the pole. How do we find the pole? Well, we can cheat and do this, and we'll see, oh, there's the North Pole. You'll notice there's a star just to the left of it, and that's actually the pole star, the North Star. The North Star is not the brightest star at night. That's Sirius. But why is this so important? How do you find it if you don't have a cheat button? Well, there's two ways of finding it. One is by finding the Big Dipper. The Big Dipper is not a constellation, it is an asterism. It is part of something much bigger. You'll see the Big Dipper is the stomach and tail of Ursa Major, the Big Bear, in the northern sky. The other object you can find, a constellation you can find, I should say, is a constellation called Cassiopeia. It is a 3 or a W or an M in the sky. It is directly opposite the Big Dipper. So if you can see the Big Dipper, you will be able to draw a line from it to find Cassiopeia. If the Big Dipper's high in the sky, Cassiopeia will be low in the sky. If the Big Dipper's in the east, Cassiopeia will be in the west. The opposite is true. If the Big Dipper's in the west, Cassiopeia will be in the east. These two are always opposite each other. Now, how do we find the North Star using these two objects? Well, let's start with the Big Dipper. 3 stars in the tail and 4 stars in the cup make up the Dipper. Again, you see the shape right in here. These last 2 stars, the pointer stars, they are about the width of your palm away from each other. You draw a line straight through them and keep going, and you will find the North Star. This distance is about the width from your pinky to your thumb. Point to Polaris. So that is Polaris, the North Star, the Pole Star. It is the tail star of of Ursa Minor, I should say, the little bear. The other way of doing this, again, is to find the triangle stars of Cassiopeia. You see one triangle there, another triangle here. You can draw a line through them like arrowheads, and you will again find the North Star about the same distance away, about the width of your hand. Away at full length. Let's put this all to orbit and rotate as we go from night to day. As you can see, these constellations never necessarily set. It all depends on where you are on the planet Earth. If you are more towards the north of our planet, so if you live, like, let's say, in Canada or, I don't know, northern Russia, the North Star is much higher up in the sky. But since where I live, we're only about 35 degrees above the horizon here. So you can see like that, it's only about 35 degrees. If we change position, we can actually do that in this dome. Let's pause it for a second. Let's say we go from where we are to Toronto. Toronto, Canada. You'll notice that the North Star is now 45 degrees above the horizon. And as you go further and further north, this will continue to happen. Let's go somewhere in Sweden, shall we? Look at how high up the North Star is, 62 degrees. So you see a lot more constellations in the sky that are along the horizon, and you see a lot more distance from the horizon to the North Star. The converse of this is true, and by that I mean if you get closer to the equator, let's return to default. There we go. Let's say we go to Miami. You'll notice that Miami, there's only about 25 degrees to get to the North Pole, the North Star. A lot closer to the equator, isn't it? I'm going to go to Puerto Rico real fast. On Juan, and you'll notice here we're very close to the horizon, and it's only 18 degrees above the horizon, so very, very little room for error when you're getting closer to the horizon, if you get closer to the equator. Let's come back to where we were before. There we go. Alright, let's let the sun set. The other thing you can do with the Big Dipper, since we're in this part of the sky, we're going to use it to find two other constellations, two other bright stars. We're going to talk about arcing with the tail. If you follow the arc of this tail, you'll notice it will arc this way towards a bright yellowish colored star named Arcturus. You arc to Arcturus. Arcturus is the brightest star in Boötes, the kinda when the world just happened. Boötes is the kind of ice cream cone shaped constellation in the sky. Ice cream cone with legs. And finally you arc to Arcturus and then spike to the south to Spica. Spica is the brightest star in Virgo, which looks like a big slug, supposed to be a beautiful maiden in the sky. Looks like a slug to me. Arc to Arcturus, spike to Spica. We will do that throughout the entire spring and summer months, so be prepared to find these two stars, and you can see them very, very clearly in the evening sky, depending on your location, of course. And they have very different colors to them. Bright blue stars are hot, bright, and not very long-lived. Red stars tend to be colder, older stars. They tend to live a lot longer unless they are what's called a red giant star. They are a special type of star, and we're going to look at all that here in just a second. Let's take a look at the other screen. All right, here we go. This is what's called the HR diagram. Hertzsprung and Russell, two astronomers that this was named after. This looks at just stars in general. We try to map out stars based on properties that we see. Luminosity is the vertical axis on the left-hand side, and then temperature is on the bottom. Now, it uses Kelvin. Kelvin and Celsius are basically the same. Not really, but for our purposes, let's just call them the same. Our sun is smack dab in the middle, and this can look slightly different depending on which chart you're looking at. There we go. You'll notice this one also has the labels, the O, B, A, F, G, K, and M. You can do it that way. There's absolute brightness over here, star brightness versus temperature. There's so many ways of doing this that they tried to squish everything together in one. We're not going to worry about that too much right now. What we're going to see here is that when you put all the stars on this kind of axis chart, they start to form a line. This right here is called the main sequence of stars. The main sequence of stars are stars that are fusing hydrogen into helium. Some stars are inherently very small. They tend to be down in this region down here. These are red stars, some of them including red dwarf stars. They are fusing hydrogen into helium, but they're not very massive, and they're not very bright, they're not very big. They tend to be kind of red in color. So you got Wolf 359, Proxima Centauri, Barnard star. They are M-class stars. They're reddish colored, very cold surface temperature for a star. Our star, the Sun, right here, is a yellow dwarf star. We consider it to be an average star, a G-class star, and has about a 10 billion year lifespan. 5 billion years down, 5 billion years to go. Everything to the right of the Sun going down this way is going to have a much longer lifespan. So more than 10 billion, so maybe 100 billion years for these stars down here. To the left of the Sun, you start getting brighter and brighter and brighter. So you can see the luminosity going up. You see the main sequence going up this way. And you see the temperature rising. So you'll see going from 3,000 degrees, this red-colored star, to our Sun, which is about 5,800 degrees on its surface, Celsius. As you go further left, you go through white stars, and you get to, like, bluish-colored stars, and then very, very blue, almost ultraviolet blue. These are very, very hot stars, but you'll notice their lifetimes are a lot shorter. And that's kind of the inverse proportion. The hotter and brighter you are, the sooner you die when it comes to a star. When stars stop fusing hydrogen into helium, they will tend to puff up and become what's called a red giant star. And they are nearing the end of their lifetime. Now, if they're a red giant, there is a possibility of them fusing other elements together. They can become slightly more stable. They'll be bigger, but they'll become stable again and fuse helium into lithium or carbon or other elements as we go along. Those stars are going to be up in here, the red giant stars. They will then kind of peter back and forth between the main sequence and the giant phase until they ultimately puff out, which is what we call, again, the Planetary Nebula. We looked at one early in the show. However, you'll notice there's another area up top called the supergiant. Those are stars that are physically huge. They are stars that, well, would take up a good chunk of our solar system if you brought the star here. We'll look at that in a second. When these stars die, we assume they're going to explode very violently, what's called a supernova remnant, supernova explosion, leaving behind a supernova remnant. Now, these regular giant stars down here, when they die, they leave behind a hot core or an ember left behind. Those tend to be called white dwarfs. They hang out right in here. They're still glowing. They're very, very hot, but they're not stars. They're just the core left over. These bigger objects, when they explode, they leave behind a very, very small, not very bright object called a neutron star. If the neutron star were to collapse, you would get what's called a black hole, an area of space that not even light can't escape it. So what does this all really mean? What does this all look like? Well, let's take a look at our universe sandbox once again. There's our solar system with the Sun in the middle. Let's pick one of these giant stars instead, just to kind of show you how physically big they can get. We've replaced the Sun with Betelgeuse, the shoulder of Orion, and you can see that this one star now takes up everything up to the orbit of the planet Jupiter. Yeah, stars can get really, really, really big. Let's get rid of all this, and let's just look at the stars on their own. That's not the one I wanted. I want a blank one. There we go. Completely blank. Let's look at stars, okay? Let's talk about the Sun. As I mentioned, there's a star called Wolf 359, which is a red dwarf star. If you're a Star Trek fan, you have heard of Wolf 359 because, well, the Battle of Wolf 359. Look at the difference between a red dwarf star and the Sun. You can tell the Sun is much brighter, and it is physically bigger. Nearby, let's put... kind of show the gamut. So we got Sirius on the left, our sun on the middle, and then Wolf 359 on the right. You can see Sirius is physically bigger, it is physically brighter, and it is much bluer. That kind of shows you how stars go. They go from really small to average size to much bigger. Now, there's the special cases that are out there. So we've got, let's see, there's Spica, which is actually a little blue star. Let's put Spica like right there. Yeah, you can see Spica is actually a little bit bigger than Sirius, I should say. There's Vega. And then there's Rigel. Rigel is a blue giant star. Still very hot, very bright, but it's physically huge. Look at all these bright blue stars. Again, physically much hotter than the sun. But there are also some smaller stars that are kind of sun-like out there that we know of. Alpha Centauri. That there, put that there. Altair, we'll put over here. Deneb, super bright, so god. Deneb is huge. I screwed that up. Let's delete Deneb. Much better. We're professionals here, folks. So here you can see again the Sun, Red Dwarf Star, Wolf 359, Alpha Centauri, and its companion. You can see Alpha Centauri is not much bigger than the Sun. But then we got to talk about giant stars. Yep, screwed that one up. Didn't give enough room. Let's try again. Here's the Sun. And there's Betelgeuse, which is gigantic. Let's put Antares, which is also a red giant star. You can see there, actually, Antares is slightly smaller. There's actually some stars that are even bigger than this, but I don't think they're in the simulation, and that's okay. They are. I lied. I believe that is the biggest star in the known universe that we know of. VV Canis Majoris, and then we've got uh-oh, where's my mouse? UY Scuti in the constellation Scutum. VY Canis Majoris. You can see these stars are huge. They are cold, though, because they are red giants. And again, if you were to just put the Sun kind of right in front of this one, which we can, you see the Sun is really small in comparison. Where's the Sun? There's the Sun. Let's go to it. There's our star, the Sun, which we think is huge and bright and all that. No. So you can see the Sun is tiny compared to this gigantic star. This is a star that's definitely going to explode at some point. Now, if a star explodes, it will be violent and cause what is called a supernova. It looks something like this. Kaboom! Star explodes and it seeds lots of gas and dust and energy into the space around it. Now, our star, the Sun, is but one of many stars in what is called the Milky Way galaxy. The Milky Way galaxy is a collection of stars, gas, dust, supernova remnants, star-forming regions, what are called stellar nurseries, all floating around in space in a spiral shape. Now, not all galaxies, as they are called, are spiral-shaped. Ours happens to be in this shape. Looks like a big whirlpool, but it doesn't look like this to us, just does it? When you look at the nighttime sky, you don't see this. When you look at the nighttime sky, you see something more like this. Because we are in the Milky Way, we are looking from a single point of light, orbiting around a single point of light, inside one of these arms. You see there are star clusters, what are called globular clusters, going vertically through the disk of the galaxy, while the galaxy itself has that whirlpool-ish shape to it. As it spins around in space. At the center is a supermassive black hole, a huge area where not even light can escape it, and it is the anchor point of our galaxy as a whole. Now, our galaxy is part of what's called the local group of galaxies. It's not alone. There's actually other galaxies nearby. You can see some of these galaxies if you live in the southern hemisphere. So if you live like in Australia or South Africa, New Zealand, things like that, Brazil, you will see the large and small Magellanic Clouds, named for Magellan, even though native peoples have always seen them. These galaxies hang out below the Milky Way. They have no real shape to them. The Milky Way is a spiral. The rest of these are going to be elliptical galaxies, or there's even this little Sagittarius dwarf galaxy right here that's more spherical. The Magellanic Clouds, we're now again in deep 3D space. There's the small Magellanic Cloud, and there's the large Magellanic Cloud right down here. Now, this is all, again, in orbit around our Milky Way. There's the Milky Way. This group of galaxies, which we call the local group, there's a bunch of galaxies kind of all orbiting around each other. At this scale, the dots you see in the background are not stars. Those are all galaxies. Very, very far away. You see some galaxies back here. You see some galaxies down here. And you see a little cluster of galaxies up here. This cluster up here is around the galaxy known as the Andromeda Galaxy, which sits in the constellation Andromeda. The distance from our galaxy to that galaxy is about 2.25 million light years, so the speed of light, or 2.25 million years. This spiral galaxy also has some companions nearby. In space, the bigger you are, the more things get attracted to you, and the more they will orbit around you. In this case, the two major gravitational forces are between the Milky Way and the Andromeda Galaxy, so in a few million years, the Andromeda Galaxy will approach the Milky Way, and we'll have a kind of a galactic fender bender. The two galaxies will quote-unquote collide, they will merge. They won't physically collide. The gravity of each galaxy will tear the other apart. This is how you get new galaxies formed. New star-forming regions will happen. Some stars and their planets will be thrown out into deep space by themselves to wander endlessly in the depths of space. Others will be formed. Others will merge into new star systems. Who knows? Things will collide, maybe. A lot of empty space between objects, but this is a simulation of what we believe will happen when the Milky Way and the Andromeda Galaxy will collide. Haunting yet beautiful. I always like to just kind of shut up and watch it at this point, so don't mind me. But yeah, there's a quick tour of our solar system and a tour of our nighttime sky. And I hopefully answered most of your questions in chat as we were going along. You didn't actually see the Milky Way collision, did you? Let's reload that. I had the wrong screen up. I see your message now, chat. I apologize. Had the wrong screen on. Here, once again, is the collision of the Milky Way and the Andromeda Galaxy. My apologies for having the wrong screen up there. Let's get rid of that circle, and you can see. There it is. There's the collision. Beautiful and elegant and terrifying all at the same time. So there's kind of a look around the sky for the evening, for the next week or so. If you're looking for your favorite planet, maybe your favorite planet's Jupiter or Saturn. My personal favorite planet is Saturn. You do have to be up early in the morning to see them. And I'm talking right before the sun comes up, so we're talking 4:30 or 5 in the morning to really be able to see them in the sky. Let's put it right here. So this is 4:30 in the morning. You will see the planet Jupiter and the planet Saturn in the sky. Jupiter will have a very distinct white, bright color to it. Saturn, however, that's not what I wanted. Saturn will have a golden color to it, and again, when you look at Saturn, even through a very small telescope, you should see something like this. You should see the ring system around it. This looks a lot better than it did in the other software, where I ended up blowing it up because I put too many particles. Jupiter, however, you will not see the rings. You will see the Galilean moons. Io, Europa, Ganymede, and Callisto. And there we go, and you see the upper atmosphere of the planet. And you see the Great Red Spot right over there, just before the sun comes up. No need to find bright stars around them, because 1, there aren't very many bright stars around them. 2, they are the brightest objects in that part of the sky. And that basically ends our show. You have fun? You enjoyed it? That's great to hear. I know I don't have chat visible for everybody else, but I do have multiple chats for me. Again, we are streaming live on Facebook and Twitch and YouTube all at the same time. I do get to see the chats kind of popping up, and I've been trying to answer questions through the lecture itself. Sometimes we do just get direct question and answers, just depends on what we're talking about. But I'm glad you enjoyed yourself. I do appreciate you stopping by and checking out my little virtual planetarium dome and my little virtual classroom. My goal is to just give people a basic astronomy education, let you learn how to find your way around the sky. And then with our pre-recorded stuff, we'll be doing lots of in-depth analyses on various planets. And doing Astronomy 101, so you don't have to go to college to take an Astronomy 101 course. All you gotta do is click on our channel and you'll get it. Slowly. There's only 2 of us working on all this. It's just myself and my wife. And if you want to include the dog and the cat, you can. So it's just a couple of us. Links to our Facebook and our YouTube, they should be in the Twitch account, or vice versa. If you're on Twitch, look for the links in the information on our channel. Same with our Facebook page. And there's also links to our Coffee account and our Patreon if you feel generous or anything like that. You feel like helping out, helping us buy some hard drives or helping us just, feed the cat and the dog or something. That is up to you. We do appreciate anything and everything that does come our way. The biggest way of helping us out is just sharing the channel and getting it to other people so that we can get more and more people interested in astronomy. Especially now, we got a lot of cool stuff happening. A lot of new observatories being built, a lot of telescopes being built for space. Mars rover. We got a moon rover from China. Got an orbiter from the UAE around Mars. European Space Agency's planning a couple of cool new probes as well. Got science happening everywhere. But this isn't always just about science. This is also about anthropology and studying human history. We all get to look at the sky, doesn't matter where we live. If you look up, you're gonna see the sky. If you're able to see, you're gonna see the sky. Lots of stories, deities, gods, goddesses, heroes. They all became constellations to watch over us or to inspire us. These constellations over time, they've inspired stories, there's literature, there's music, song, paintings, all because of one science, all because of astronomy. I try to use this to inspire all of you. So with that, we're gonna call it a day. We hope you enjoyed our show. We will see you on Friday, and if anything changes with the Mars Ingenuity, if they decide to launch earlier, we will, of course, go live to watch that, and we'll restream it here, but as far as I can tell, it's not happening until next week, so we'll just take care of that next week. Alright? Alright, everybody. Have a good afternoon, evening, morning, wherever you happen to be. We will see you next time. We appreciate you stopping by. Take care of yourselves. Take care of each other. See ya.